Good morning, sir. I am Saiteja from Tribly Department. Today, AIT topic is about power MOSFET, switching behaviors and uses cases. Introduction to power MOSFETs. Basic concept and architecture. Definition and function. A power MOSFET, metal oxide semiconductor field effect transistor, is a voltage control device used to switch and amplify electrical power efficiency in highly high frequency circuits. Structure overview consists of source, drain, and gate terminals with a vertical structure optimized for low on resistance and high current handling. Power versus signal MOSFET. Power MOSFETs are engineered to handle large currents and voltages, unlike signal MOSFET, which operates at low power level. Key use domains widely used in motor drivers, power supply power supplies, converters, and high frequency applications due to fast switching and high efficiency. Key parameters of MOSFETs: electrical and thermal performance indicators. On resistance RDS defines the resistance between drain and source when MOSFET is on. Lower RDS on improves efficiency and reduces heat. Threshold voltage minimum gate voltage required to start conduction, impact compatibility with gate drivers, and noise immunity. Gate charge total charge needed to fully switch the MOSFET. Effects switching speed and drive requirement. Body diode performance. Instack diode effect reverse recovery and conduction losses in synchronous applications. Switching characteristics of power MOSFETs. Dynamic behavior and dimming definitions. Turn on and turn off. Gate drives requirement. Switching waveform. Parasitic effect. Turn on and turn off. Involves charging, discharging gate capacitance. Turn ons delays rise time, fall time, and turn off delay defines the transistor. Transitions. Gate drive requirement. Switching behavior depends on the strength and speed of the gate drivers. Inductive driving leads to slow transition and power losses. Switching waveform. Drain voltage and current curves during transition shows overshoot, ringing, and dimming intervals critical for design. Parasitic effect. Parasitic inductance and capacitance impact switching speed and can induce oscillations. Losses in switching power MOSFET. Conduction transition and thermal losses mechanism. Conduction losses occurs when MOSFET is fully on proportional to I square RDS. Lower on resistance reduces heat and improves efficiency. Switching losses occur during transition period. Overlaps of voltage and current causes significant power dissipation. Hard and soft switching. Hard switching incurs higher losses and EMI. Soft switching uses resonant techniques to minimize energy losses. Thermal management. Heat sinks, thermal wires, and carefully layout are needed to dissipate heat and maintain reliability. These are the losses in the switching power of MOSFET. For MOSFET in practical circuits, topology and real-world integration, DC to DC converters, bridge inverters, synchronous rectifiers, lighting and inductive load. DC to DC converters. MOSFET switches powers in buck, boost and buck boost converters controlling output voltage in power supply. Bridge inverters used in full bridge and half bridge topology for motor drivers and AC power generation from DC source. Synchronous rectifiers. MOSFET replace diodes to reduce conduction losses in high efficiency power supply. Lighting and inductive load. Power MOSFET handles switching for LED drivers and inductive loads with high transient tolerance. Applications case studies. Power MOSFET in industries and consumer system. Switch mode power supplies SMPS, electrical vehicle powertrain, wireless power transfer, renewable energy system, switch mode power supply SMPS used in AC to DC and DC to DC conversion for efficiency and size reduction in computers, telecom, and consumer electronics. Electrical vehicle powertrain. MOSFETs controls motors, battery charging, and inverters in EVs, emphasizing fast switching and regulateness. Wireless power transformer enables high frequency operation in resonance inductive or capacitive wireless charging system. Renewable energy system used in solar inverters and battery charges controllers to manage high voltage and current fluctuations. Design consideration of power MOSFET, layout, drives, and system integration. PCB layout minimize loop areas to reduce EMIs, use wide dries for low resistance and good thermal conduction. Gate drive selection, choose drivers with fast rises, fault time, and sufficient current sourcing for fast switching. Thermal management, use heatsink, thermal via and copper planes, ensure good junction to ambient heat flow. Paralleling and derating. When using multiple MOSFETs in parallel, count for current sharing and thermal imbalance. Emerging trends in power MOSFETs. JAN, SIC, integration and smart system. SiC devices offer superior performance in high voltage, high frequency application with low losses and faster switching. High frequency operation emerging devices enable megahertz level switching, reducing passive sites and improving transient response. Integrated power stage. Power MOSFETs are being integrated with drivers and controller for compact efficient modules. Intelligent system. Smart MOSFET with telemetry protection and fault reporting, enhanced reliability, and MOSFET gate drives techniques. Totem pole drives, common in low-side driving, provide fast transition using complementary BJTs or MOSFET. Bootstrap techniques enables high-side driving using a diode and capacitor, compact and cost-effective for synchronous circuits. Isolated gate drives, used when galvanic isolation is required based on transformer or optocoupler. Should to prevention, D-time insertion and UVLO prevents simulation conduction in half-bridge protection MOSFET. Failure mode and protection strategies. Avalanche breakdown, thermal runaway, latch up and gate over streets protection circuit. These are the failure modes and protection strategies of the ensuring longevity and safety power of MOSFET. Comparison Comparison MOSFET and IGBT. Switching speed. MOSFET switches faster, ideal for high frequency converters. IGBT is slower but handles higher voltages. Conduction losses. MOSFET have lower RDS on losses at low voltages. IGBT dominates in high voltages, high current uses. Cost and integration. MOSFET supports small integrated design. IGBTs are bulkier and but cheaper per watt in large system. Application suitable MOSFET, SMPS, EVs, RF, IGBTs, industrial drives, weldings, UPS, grid-tied inverters. Selection criterion, datasheet analysis, voltage and current rating, RDS on and QG rates of thermal rating and practical evaluation. Case study, synchronous buck converters, MOSFET roles, waveforms and design insight, topology overview. Uses high side and low side MOSFETs for efficient DC to DC conversions. Operates in continuous mode. Switching behavior. High side MOSFET conducts during on time. Low side synchronous MOSFET replace diode during turn off. Losses analysis. Key losses include switching conclusion and body diode recovery optimized by MOSFET selection. Thermal design and layout. Thermal wires, copper pan and minimal switch mode loops reduces heat. Layout optimization for high-speed switching, minimize loop areas, use ground plane, Kelvin source connections, thermal and EMI balance. These are the layout optimization for high speed switching, MOSFET body diode behavior. Body diode characteristic. Built-in diode in MOSFET conducts during reverse current flow as high VF threshold voltage than Schottky diode. Reverse recovery charges stored during conduction and removed upon turning off leads to current spikes and noise losses and heating. Reverse recovery contributes to switching losses and heat that die significantly. Alternatively, optimization. Use of synchronous rectification Schottky diodes improves performance in critical path. High voltage design techniques, snappiness circuits, insulation coordinate, voltage rating, creepage, and clearance. Simulation and modeling, spice modes, loss simulation, thermal modeling, waveform analysis. These are the simulation and modeling for MOSFET. Reliability and lifetime estimation. Regularity standard in power electronics. EMIs and EMA stands like CISPR 22 or 32, EN 55011 by regulates electromagnetic emission and immunity. Safety standard UL, EC and ISO standard ensures product safety under electrical thermal stress testing and certification. Pre-compliance testing and certified label ensures adherence to market regulation. Conclusion and best practices. Switching optimization. Balance speed and efficiency by turning gate drives strength and managing practices. Thermal and EMI use proper layout, cooling and snapdowns to handle losses and suppress noises. Application specific design. Select MOSFET based on voltage, current, switching, speed and packaging requirements. Stay current with technology. Leverage emerging material, smart futures and integrated power stages for future ready design. Thank you.